Welcome to TyroHero's documentary series. Today we're exploring the man who sorted the universe, a brief history of Dmitri Mendeleev. Imagine waking up from a dream, and inside that dream, you saw the entire universe organized. Every building block of matter, every element, every atom, arranged in a perfect, elegant grid. That's exactly what happened to one man in the winter of 1869. His name was Dmitri Ivanovich Mendeleev, and what he created didn't just change chemistry. It changed how humanity understands the very fabric of reality. Now, before we dive in, think about this for a moment. Right now, everything around you, your phone, your clothes, the air you're breathing, the blood moving through your veins, is made of elements, about 100 of them. And for most of human history, nobody knew how many elements there were, or whether they followed any kind of order at all. Ancient Greeks thought everything was made of just 4 things: earth, water, fire, and air. By the 1800s, scientists had identified dozens of distinct elements, but they were a confusing jumble with no obvious system. It felt a bit like trying to read a library where all the books had been thrown on the floor with no shelves, no catalogue, no order. One man changed that. One man looked at the chaos and saw the pattern hiding inside it. Today, we're going on a journey. From a freezing Siberian village through the revolutionary scientific circles of 19th century Europe to the corridors of power in St. Petersburg, and finally to a moment of pure genius that would echo through history forever. This is the story of the man who sorted the universe. To understand Mendeleev, you have to understand the world he was born into, because it shaped everything about him. It was 1834. Russia was a vast, sprawling empire ruled by Tsar Nicholas I, a man who believed firmly in autocracy, military discipline, and the suppression of new ideas. Science existed, but it existed in service of the state. Chemists were useful if they could improve gunpowder or agriculture. Curiosity for its own sake was viewed with suspicion. Siberia, where Mendeleev was born, was simultaneously Russia's wild frontier and its dumping ground. Political prisoners were sent there. Exiles lived there. It was thousands of miles from Moscow, with brutal winters, rudimentary roads, and an economy built on agriculture and small industry. But Siberia also had something else, a certain independence of spirit. People there had to be resourceful, tough, and self-reliant. Those traits would prove to be deeply embedded in Mendeleev's character for the rest of his life. Meanwhile, in the wider scientific world, chemistry was undergoing a kind of identity crisis. Dozens of new elements had been discovered in the past century: oxygen, hydrogen, nitrogen, chlorine, sodium, potassium. A flood of new substances with no clear organizing principle. Was there a pattern? Were there rules? Nobody knew. Some scientists had tried to find order. In 1817, a German chemist named Johann Wolfgang Dobereiner noticed that certain elements came in groups of 3. He called them triads, where the middle element had properties exactly between the other 2. Calcium, strontium, and barium, for instance, or chlorine, bromine, and iodine. It was a clue, a hint, but nobody knew what to do with it yet. An English chemist, John Newlands, tried in 1865. He arranged the known elements by atomic weight and noticed that every 8th element seemed to have similar properties. He called it the law of octaves, like notes on a musical scale. His colleagues laughed at him. One of them sarcastically asked if he had tried arranging the elements alphabetically. It was not a kind moment for science. The pieces were there. The pattern was hiding in plain sight. It just needed someone with the right mind and the right obsession to finally see it. Dmitri Mendeleev was born on February 8, 1834, in the small Siberian town of Tobolsk, a former fur trading capital that had seen better days, now a modest provincial town roughly 1,400 miles east of Moscow. He was the youngest of somewhere between 11 and 17 children. Yes, you heard that right. Historical records vary on the exact number, but his mother, Maria Dmitrievna, had an extraordinary family, and Dmitri was the last, the baby of a very large, very loud household. His father, Ivan Pavlovich Mendeleev, was the director of the local gymnasium, a type of academic secondary school. He was an educated man, a teacher, a figure of intellectual standing in the community. The young Dmitri grew up surrounded by books, ideas, and the value of learning. But then, disaster. When Dmitri was still a small boy, his father went blind from cataracts. He lost his teaching position. The family's main income vanished almost overnight. In Siberia in the 1830s, there were no safety nets, no government assistance, no backup plan. His mother, Maria, rather than collapsing under the weight of this crisis, took action. She revived and ran an old glass factory that had belonged to her family, managing workers, handling finances, learning the business side of industry with the kind of grit that would later appear, unmistakably, in her youngest son. For a few years, the factory kept the family afloat. Then the factory burned down. Then Ivan Mendeleev died. Maria Mendeleev was now a widow. She was penniless, in Siberia, with a house full of children, and one of them, the youngest, was clearly special, clearly different, clearly destined for something that Tobolsk could not provide. She made a decision. She would get Dmitri to a university, no matter what it cost. So she packed up what remained, gathered her youngest son and her eldest daughter, who was also talented and needed education, and walked them to Moscow. Not metaphorically. She organized a journey of over 1,000 miles to the Russian capital. The university in Moscow refused to admit him. He was from Siberia, wrong region, wrong district. The rules were the rules. They turned him away. Maria did not stop. She pressed on to St. Petersburg, Russia's imperial capital, its scientific center, the home of its finest institutions. She enrolled Dmitri at the main pedagogical institute, the very same school his father had attended a generation earlier. And then, having crossed a continent on foot and by cart, having knocked on every door that needed knocking, having refused every refusal, Maria Mendeleev died. Dmitri was 15 years old, alone, grieving, in a strange city. His mother's last act on this earth had been to put him in a position where his gifts could flourish. He would carry that with him for the rest of his life. In later years, he wrote, "She instructed by example, corrected with love, and in order to devote him to science, she left Siberia with him, spending her last resources and strength." Whatever Mendeleev built, he built on that foundation. After his mother passing, and the recent accepted enrollment into the institute, Mendeleev threw himself into his studies with a ferocious, almost desperate intensity. He excelled in mathematics, physics, and chemistry, earning some of the highest marks. But those early years were genuinely difficult, both intellectually and emotionally. He was lonely, he was poor, he was grieving, and he was, by some accounts, not particularly easy to get along with, blunt, opinionated, and absolutely certain of his own judgments in a way that alienated some classmates and charmed others. As time passed and he was consumed by his studies, he eventually fell direly ill. By his early 20s, doctors were diagnosing him with tuberculosis, a disease that was a death sentence as often as not during the 1800s. The medical staff had recommended to the institute to send him south to Crimea, along the Black Sea coast, where the warm air might slow the disease's progress. While living and working as a science teacher in Crimea, Mendeleev became so respected by the local educational community that administrators actively tried to keep him there permanently. He had arrived as a sick, grieving student from Siberia and left as a highly celebrated intellectual. Even at 22 years old, the man had a gravity that drew people in. He returned to St. Petersburg in improved health and earned his master's degree in 1856. Then, In 1859, he won a prestigious government fellowship to study abroad in Heidelberg, Germany. Heidelberg at that time was the scientific capital of the world. Robert Bunsen, the creator of the widely used Bunsen burner across classrooms globally today, was there. Gustav Kirchhoff, who would help found the science of spectroscopy, was there, as well as many other well-renowned scientists and researchers during the height of their career. The air practically crackled with discovery. Mendeleev set up his own small private laboratory in his apartment, rather than working in the university's facilities, a telling choice. He wanted to do things his own way, on his own terms, from the very beginning. He studied the surface tension of liquids, investigated capillary action, and conducted careful experiments on the behavior of gases. He was building a comprehensive understanding of physical chemistry, not just memorizing facts, but developing the kind of deep physical intuition that would later allow him to see what others couldn't. And then came the event that would, in retrospect, plant the seed of his greatest achievement. In September of 1860, Mendeleev attended the first International Congress of Chemistry in Karlsruhe, Germany. It was the first ever international gathering of chemists, about 140 scientists from across Europe meeting to argue about definitions, standards, and the very foundations of their field. The central debate at Karlsruhe was about something that sounds technical, but is actually profound. What exactly is an atom, and how should we measure atomic weight? Different chemists had been using different values for atomic weights, which meant the same formula meant different things in different labs. The chaos was real, and it was slowing down all of chemistry. At Karlsruhe, an Italian chemist named Stanislao Canizzaro distributed a pamphlet presenting a clear, consistent method for determining atomic weights, building on the earlier work of Amedeo Avogadro. Mendeleev read it, and something clicked. If you had a consistent, reliable set of atomic weights for every element, accurate numbers you could actually trust, what could you do with them? What patterns might emerge? Mendeleev returned to St. Petersburg in 1861 and plunged right back into academic life. He was appointed professor at the St. Petersburg Technological Institute, and a few years later took a second professorship at St. Petersburg State University. He was teaching, researching, writing, operating at full speed all the time. He also married. His personal life was, to put it charitably, complicated. He married his first wife, Fyodora Nikitichna Leshova, in 1862, but the marriage was unhappy from early on. They had 2 children, but by all accounts the relationship was cold and distant. Mendeleev was not easy to live with. He was consumed by his work, mercurial in temperament, and as stubborn as a stone wall when he believed he was right. Years later, he would fall passionately in love with a young art student named Anna Ivanova Popova, and in a move that scandalized Russian society, he divorced his first wife and married Anna before the Orthodox Church's required waiting period had elapsed. The Tsar was reportedly asked to intervene. He declined. Mendeleev married Anna, and that was that. But we're getting ahead of ourselves, because first, there was a textbook to write. In 1867, Mendeleev was preparing his chemistry lectures and realized with mounting frustration that there was no adequate Russian-language chemistry textbook. The existing options were translations of outdated foreign texts, or thin volumes that covered only parts of the subject. His students deserved better. So, he decided to write one himself. He called it The Principles of Chemistry, Osnovy Chemii in Russian. His plan was comprehensive: cover every known element, its properties, its compounds, its behavior. A complete map of chemical knowledge as it stood in 1867. And here is where the puzzle started to assemble itself. As he began organizing the textbook, deciding which elements to cover, in what order, in what groupings, he kept running into a problem. How do you organize them? Alphabetically? By discovery date? By how common they are? None of those approaches made scientific sense. He started arranging them by atomic weight,
those reliable numbers that Cannizzaro had helped establish at Karlsruhe. And as he did, the patterns he had vaguely sensed for years started coming into sharper focus. Lithium, sodium, potassium, all soft metals, all react violently when dropped in water, some so violently they explode. Arranged by atomic weight, 7, 23, 39. The gaps aren't equal, but the behavior is unmistakably the same. Fluorine, chlorine, bromine, iodine, all halogens, sharp, corrosive, toxic. Arranged by atomic weight, 19, 35.5, 80, 127. Different numbers, same chemical family. The pattern was there. The properties repeated, not randomly, but at regular, predictable intervals, like a melody that plays in a different key but is unmistakably the same tune. He began writing element names on individual cards, one card per element, with its atomic weight and key properties. He spread them out, moved them around, rearranged them obsessively. He was looking for the grid, the hidden architecture beneath the apparent chaos. For months he worked, teaching his classes, writing his textbook, and always returning to those cards.
February 17th, 1869. Mendeleev had been working for days without adequate sleep, writing, arranging, rearranging, filling pages with numbers and element names and arrows and question marks. And then, at his desk, he fell asleep. He later described what happened. I saw in a dream a table where all the elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction later seem necessary. Now, historians and scientists debate how literally to take this story. Some argue it's a polished legend, a good story that simplified a longer process. Others point out that Mendeleev repeated this account consistently throughout his life and had no reason to fabricate it. What the evidence does show is this. On the morning of March 1st, 1869, by the modern calendar, Mendeleev drafted a single-page document laying out his proposed system. It was a grid, rows and columns, 63 known elements arranged by atomic weight, with similar elements falling into the same vertical columns. He sent it to the Russian Chemical Society and arranged for a colleague named Nikolai Menshutkin to present it at their meeting, because Mendeleev himself had an appointment to inspect a cheese-making cooperative in the countryside. Yes, he was inspecting dairy farms the day his periodic table was first presented to the world. The title of his paper, The Dependence Between the Properties of the Atomic Weights of the Elements. The paper announced his periodic law. The properties of elements are a periodic function of their atomic weights. In other words, arrange the elements in order of increasing atomic weight, and their properties repeat on a regular cycle. This was not just a neat organizational trick. It was a law of nature, a claim that the universe itself was structured this way, that matter wasn't random, that the elements had a deep underlying order that human reason could discover and describe. The table he presented was a grid, rows called periods, columns called groups. Elements in the same group shared similar chemical behaviors. Moving across a row, the properties changed gradually but predictably. Moving down a column, you saw the same personality expressed at larger and larger atomic scales. But the most extraordinary thing Mendeleev did, the thing that separated his table from everyone else's attempts, was this. Where the logic of the table demanded an element should exist, but no element had yet been discovered to fill that space, Mendeleev did not fudge the numbers or skip the slot. He left it blank. And he went further. He predicted the properties of those missing elements in detail. He left gaps. He predicted their atomic weights, their densities, the color and texture of their metals, the compounds they would form, even how they would behave in chemical reactions. He described 3 undiscovered elements with enough precision to give them placeholder names: Eka boron, Eka aluminum, and eka-silicon. In Sanskrit, eka means one, as in one step beyond. He was saying, beyond boron, there is an unknown element. Beyond aluminum, another. Beyond silicon, another still. And here is exactly what they will be like. It was either the most audacious prediction in the history of science, or the delusion of a man who had been working too hard and sleeping too little. The world would find out. Before we get to the vindication, it's worth pausing to ask a fair question. Was Mendeleev really the only person who found this pattern? Because history, as it turns out, is more complicated than a single genius moment. A German chemist named Lothar Meyer had independently arrived at a very similar table at almost exactly the same time. His work was rigorous, careful, and essentially correct. He even published a periodic table in 1870, just a year after Mendeleev's first paper. For decades, there was genuine controversy over who deserved the credit. Meyer was gracious about it. He acknowledged Mendeleev's priority on the published prediction, and the scientific community eventually settled on Mendeleev as the primary figure for a specific reason. Meyer did not leave the gaps. He did not predict the missing elements. He saw the pattern and mapped the known world. Mendeleev saw the pattern and predicted the unknown world. That difference, the audacity to say, there are things we haven't discovered yet, and here is what they will be, is what made Mendeleev's version a scientific breakthrough rather than just an organizational system. It is also worth acknowledging the work of Alexandre-Émile Béguyer de Chamcourtois, a French geologist who, in 1862, arranged the elements on a spiral around a cylinder and noticed the periodic repetition of properties. He called it the telluric helix. His paper was largely ignored, partly because it was published without the diagram that would have made it comprehensible. And then there was poor John Newlands, the Englishman who had been mocked for his law of octaves in 1865. When it became clear, after Mendeleev's triumph, that Newlands had indeed been on the right track, the Royal Chemical Society had to rather sheepishly award him the Davy Medal in 1887, more than 2 decades after laughing him out of the room. Science, it turns out, is not always kind to those who are right too early. Mendeleev's timing and his predictions gave the world something it could test and verify. That made all the difference. The scientific community's initial reaction to Mendeleev's table ranged from polite skepticism to outright dismissal. After all, he was claiming not just to organize chemistry, he was claiming to know what hadn't been discovered yet. That's a bold claim. Maybe too bold. Then, in 1875, a French chemist named Paul-Émile Lecoq de Bois-Baudron was studying zinc ores from the Pyrenees Mountains when he noticed spectroscopic lines he didn't recognize. Something unknown was emitting those lines. He isolated it. He named it gallium, after Gallia, the Latin name for France. Mendeleev read the discovery announcement and immediately recognized his eka aluminum. He wrote to Bois-Baudron with a remarkable message, essentially saying, "The density you measured seems slightly off. I believe the true density is closer to 5.9. Please check again." Bois-Baudron, somewhat taken aback that a Russian chemist was telling him his own experimental results were wrong, remeasured. Mendeleev was right. Let's look at the actual numbers because they are genuinely astonishing. Mendeleev had predicted atomic weight of about 68. Gallium's actual atomic weight, 69.7. Predicted density, 5.9. Actual density, 5.91. Predicted melting point, low, possibly below body temperature. Actual melting point, 29.8 degrees Celsius, so low that gallium melts in the palm of your hand. The scientific world took notice. Then, in 1879, Swedish chemist Lars Fredrik Nilsson discovered scandium, Mendeleev's eka boron. Nilsson himself wrote that Mendeleev's prediction and his discovery fit with remarkable accuracy. Predicted atomic weight, 44. Actual, 44.96. Predicted oxide formula, Es2O3. Actual, SC2O3. Exact match. And in 1886, German chemist Clemens Winkler discovered germanium,
the eccentric. Winkler was so struck by the precision of the match that he wrote it was difficult not to feel a kind of mystical reverence for Mendeleev's prediction. Predicted atomic weight, 72. Actual, 72.63. Predicted density, 5.5. Actual, 5.35. Predicted specific heat, 0.073. Actual, 0.076. 3 predictions, 3 confirmations, all within a decade and a half. The periodic table was not a filing system, it was a map of reality, and it had blank spaces waiting to be filled by the universe itself. Mendeleev's fame exploded. He was celebrated across Europe and Russia. The man who had been turned away from a Moscow university was now receiving honorary degrees from Oxford, Cambridge, Princeton, Göttingen, and dozens of other institutions. He was elected to scientific societies across the continent. He was nominated for the Nobel Prize in Chemistry, twice. Both times he was passed over, partly due to academic politics and the fact that the Nobel Committee felt his work was too old, having been done decades before. It remains one of the more controversial omissions in Nobel history.
After Mendeleev's landmark paper, the table continued to evolve, and some of those evolutions revealed both the power and the limits of his original vision. One of the most significant challenges came in the 1890s, when a new family of elements was discovered that Mendeleev had not predicted at all: the noble gases. Argon, helium, neon, krypton, xenon. Chemically inert, they didn't react with anything. They fit no existing group in his table. Mendeleev, initially skeptical that they were elements at all, eventually accepted them, and they were slotted into a new group at the far right of the table called Group 18. The table accommodated them gracefully. Its architecture was flexible enough. The deeper revision came in 1913, when a young British physicist named Henry Moseley used X-ray experiments to discover that what really defines an element is its atomic number, the number of protons in its nucleus, not its atomic weight. When the table was reorganized by atomic number, a few of the awkward anomalies in Mendeleev's arrangement resolved themselves perfectly. But here's the key thing: the fundamental structure didn't change. The rows, the columns, the repeating periods, the element families, all of it remained exactly as Mendeleev had laid it out, because his intuition had been right, even if the theoretical foundation had to be rebuilt beneath it. The modern table now contains 118 confirmed elements. The last 4 were officially named in 2016. Element 101 is Mendeleevium, a radioactive synthetic element created in 1955, named in his honor. It has a half-life of about 51 days and exists only in particle accelerators. But it sits in the table he built, carrying his name into the heart of matter itself. By the early 1900s, Mendeleev was an old man, bearded, legendary, still working, still arguing with anyone who disagreed with him about anything. He had outlived his mother, his first marriage, multiple scientific controversies, and 2 Nobel Prize snubs. He had found late happiness with his second wife, Anna, with whom he had 4 children and a genuinely warm, devoted partnership. His later years were spent at the Bureau of Weights and Measures, corresponding with scientists around the world, writing, revising, thinking. He was, by all accounts, not mellowed by age. He remained opinionated, stubborn, and passionately curious until the very end. Dmitri Ivanovich Mendeleev died on February 2nd, 1907, just 6 days before his 73rd birthday. The cause was influenza. At the time of his death, students in St. Petersburg carried copies of his periodic table in procession behind his coffin. He had started life as the youngest child of a blinded schoolteacher in Siberia, brought to the edge of civilization by a mother who believed in him completely. He ended it as one of the most celebrated scientists in the history of the world. The periodic table hangs in virtually every chemistry classroom on Earth. It's printed on posters, painted on murals, worn on t-shirts, tattooed on arms. It's become the most universally recognized scientific diagram in human history, but its legacy goes far deeper than decoration. The periodic table is a working tool that chemists, physicists, engineers, and material scientists use every single day. When researchers design new medicines, they think in terms of the table. How will this element bond with that one? When engineers develop new battery technologies, they're navigating the table's landscape of reactivity and conductivity. When astrophysicists model the interior of stars, they use the table to predict what elements will form under what conditions. Every smartphone contains elements that Mendeleev either identified or predicted: cobalt, lithium, indium, neodymium. Every drug in your medicine cabinet was designed using principles that flow from the periodic table. Every LED, every solar panel, every fiber optic cable, all of it traces back to a grid drawn up by a Siberian professor in 1869. But perhaps the most profound legacy of Mendeleev's work is philosophical. He demonstrated, with startling clarity, that the natural world has deep, hidden order, that the universe isn't random, that human reason, applied with enough patience and rigor, can discover the rules that govern reality. He showed that science isn't just cataloging what exists, it's predicting what must exist, that the gaps in our knowledge are not failures but invitations. And he showed all of this starting from a Siberian village, a mother's sacrifice, and a dream about a table where everything finally fell into place. Dmitri Mendeleev didn't just give us a table, he gave us a way of seeing, a proof that the natural world has deep, hidden order waiting to be discovered by anyone patient and curious enough to look. Thank you for watching this mini documentary and story about the amazing life of Dmitri Mendeleev, brought to you by TyroHero, where we focus on education, learning, and discovering the beauty of the natural world. If you enjoyed this story, hit subscribe. There are more extraordinary lives and world-changing discoveries waiting for you here every week. Drop a comment below. Which element is your favorite and why? Until next time, stay curious.